Hey, this section is all about differentiating the exponential and logarithmic functions. Now, the first video is going to get a little bit messy as we define the exponential function e to the power of x. If you don't follow all the details, don't worry entirely. The whole point of this is not to put you off, but rather just to give you a little bit of insight into it. But hey, it gets pretty messy, and if you don't like it, you don't really need to know that much of it. What you do need to know is the result at the end, and I will put a box around that, so don't worry. Okay, so first of all, we're going to define this mysterious number e, and we're going to say that e is equal to the limit as n tends to infinity of the function 1 plus 1 divided by n to the power of n. So we're saying as n gets bigger and bigger, if this thing gets closer and closer to some number, that's what the number e is equal to. And we're going to suppose that it exists for now. We'll show that it exists soon, don't worry. So now we're going to take e to the power of x. Well, based on this definition, we have that e to the power of x must be equal to this limit as n gets closer and closer to infinity. What I mean by that is as n gets bigger and bigger of 1 plus 1 divided by n to the power of n, and then we're taking that thing to the power of x. Okay, well, we can bring it inside the limit now. So this is equal to the limit as n gets closer and closer to infinity. Remember, we're supposing that this limit here inside the brackets exists. So if that limit does exist, then when we take it to the power of x, it's the same as just taking all those 1 plus 1 over n to the n's to the power of x and seeing what happens as n gets bigger and bigger. Okay, so this should be equal to the limit as n tends to infinity of 1 plus 1 divided by n to the power of n, and then that thing to the power of x. And if we're taking a power of a power, you just have to multiply the powers. So this is equal to 1 plus 1 over n to the power of n times x. Remember, if you're taking a power to a power of another power, you can actually just multiply those two powers, so we don't need those brackets. Okay, and now we're gonna suppose x is bigger than 0. There's only a minor modification needed if x is smaller than 0. So let's just suppose x is bigger than 0 for now, and let u, the letter u, equals nx. And then nice things are going to happen. So in that case, if x is bigger than 0 and u is equal to nx, then we can see that as n gets bigger and bigger, as n tends to infinity, we can see that u tends to infinity. So therefore, this limit is actually equal to the limit as u tends to infinity of 1 plus 1 over n. Well, if u is equal to nx, then n is equal to u divided by x. So this is equal to the limit as u tends to infinity of 1 plus 1 divided by u divided by x. But 1 plus 1 divided by u divided by x, well, that's just equal to 1 plus x divided by u. And we're taking this to the power of nx, so that's to the power of u. And then finally, well, we can just relabel it now because it doesn't matter whether we call it u or n, it's still the same thing. So this is equal to the limit as n tends to infinity of 1 plus x divided by n to the power of n. And so that's equal to e to the power of x. Okay, so e to the power of x for any number x that's bigger than 0 is equal to the limit as n tends to infinity of 1 plus x divided by n to the power of n. And that's provided, of course, that this limit exists. But we're going to show that this limit here exists for any x, and therefore it's also going to exist up here because in the first one, that's just e to the power of 1, and here x is equal to 1. Alright, let's go ahead and do that right now. So we're going to use a new board, and we're going to do it by expanding out what we just had there. So we're actually going to expand out, so let's suppose n is finite for now, and we're going to expand out 1 plus x divided by n to the power of n. We're going to expand this thing using the binomial theorem. If you don't remember the binomial theorem, go and watch that video I made about the binomial theorem. It will explain this entirely. So 1 plus x divided by n to the power of n is equal to 1 plus n choose 1 times x divided by n plus n choose 2 times x squared divided by n squared plus, and we keep going until we get to x to the power of n divided by n to the power of n. So remember, since we're multiplying everything by 1 anyway, it's like 1 to the power of 2, 1 to the power of 3. These are all 1, and so I don't even need to bother writing those in. Okay, well, we're going to simplify this part now. Remember that n choose k is equal to n factorial divided by n minus k factorial times k factorial. That's going to be important here. So this is equal to 1, so that's the first one there, plus, or n choose 1 is just n, so 1 plus n divided by n, well, 1 plus nx divided by n, so that's just x, plus, and now it's going to be, oops, that's a horrible plus, plus n factorial x squared divided by 2 factorial times n minus 2 factorial n squared plus n factorial times x cubed divided by, so this is n choose 3 now, even though I didn't write it up here, I'm going to do more terms down here just to make it clearer. So this is n factorial x cubed divided by 3 factorial times n minus 3 factorial times n cubed. And then we keep going, plus, dot, 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 plus. And then at the end, this x to the power of n divided by n to the power of n is actually the same as n factorial x to the power of n divided by n factorial n to the power of n. So notice that these n's are going up in power as we go along. And also the x's are going up in power as we go along. And also these factorials here are going up in power as we go along. So those are important observations to make. We're going to do a bit of simplification now. First one, this n divided by n cancels, so we just get 1 plus x. And now, well, n factorial divided by n minus 2 factorial. So n factorial is n times n minus 1 times n minus 2 times n minus 3 times and so on. In other words, it's n times n minus 1 times n minus 2 factorial. So those n minus 2 factorials will just cancel off and we'll be left with n times n minus 1 on top. Oops, x squared. Divided by, and then down here we still got 2 factorial. We canceled the n minus 2 factorial off. That's where the rest of this stuff went. Cancel the n minus 2 factorial off, and we've still got n squared on the bottom. Plus, same deal again. We're going to cancel some parts of this off because we got n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times n minus 4 and so on. In other words, it's n times n minus 1 times n minus 2 times n minus 3 factorial. Well, we're going to cancel the n minus 3 factorials off. So it's actually just n times n minus 1 times n minus 2 on top times x cubed divided by, and now we're going to leave the n minus 3 factorial out because we canceled that away. So divided by 3 factorial times n to the power of 3. Plus, let's do one more just to kind of make it clearer what's going on. So plus the fourth one, which again, I didn't write it here, but I'm going to do another one down here just to make it clearer. So plus n times n minus 1 times n minus 2 times n minus 3 x to the power of 4 divided by 4 factorial times n to the power of 4 plus, and we keep going, and this last one well, it's going to be n times n minus 1 times dot 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 times, and it's going to go all the way down to n minus 1. N minus n minus 1, and we're going to have x to the n on top, and we're dividing that by n factorial on the bottom times n to the power of 4. Sorry, n to the power of n. n to the power of 4 was the last one. All right, so that's where we're at so far. Now we're going to expand these out. Now we're going to expand some of them out. So far, we've still got 1 plus x. Oops, phone's ringing. Okay, sorry about that. So we've still got 1 plus x. So 1 plus x plus, and now when we expand this one out here, we get n squared minus n, and we're still timesing that by x squared, and this is still divided by 2 factorial times n squared, plus, well, n times n minus 1 times n minus 2 times x cubed. Oh, right, we're expanding it up. Plus, what does that expand out to? N cubed, I did this earlier, n cubed minus 3n squared plus 2n x cubed divided by 3 factorial n to the power of 3 plus, and so on. Well, plus, I'll do one more, n to the power of 4, so that's this one expanded out now. So plus n to the power of 4 minus 6n cubed, I'm running out of room here, plus 11n squared minus 6n x to the 4 divided by 4 factorial n to the 4, and so on. So plus dot dot dot. We keep going. I'm not going to bother expanding out. This one. That would take ages. I can't be bothered to write down the formula for that because it's not that important. However, some important things that we do need to notice are the following. All of the first terms are going to cancel with the term on the bottom. So for example, on top we've got n squared. That's going to cancel with n squared down here. So we're just left with x squared divided by 2 factorial. Similarly here, n cubed divided by n cubed is 1. So we're just going to be left with x cubed divided by 3 factorial. And similarly here, we got n to the 4 divided by n to the 4. So on top, we're just going to be left with x to the 4. Sorry, that 4 looks a bit wonky, but that's going to be n to the 4 times x to the 4 divided by n to the 4. So we're just left with x to the 4 divided by 4 factorial, and so on. So you're seeing a pattern here, and we're adding all these together. So, and I'm going to need a new board. So what we're going to have is actually 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4 divided by 4 factorial plus, and we keep going like this all the way up to x to the n divided by n factorial. Are we done yet? Absolutely not. There is more. So we need to go back and have a look at what else there is. Well, okay, another important thing to notice is that for the second term is always going to be negative. Why is the second term always going to be negative? Because for the second term, we're always going to be multiplying by one negative number, and the rest of them are all multiplied by n. So there's always going to be one negative number, but the rest of them are all multiplied by n. So it's going to be a negative times the rest positive. So we're always going to have a negative second term. And it's always, the second term is always going to be one less power than the one on the bottom. So most of the n's will cancel out. So that one will cancel with one of those n's. So our first term will be negative x squared divided by 2 factorial n. So let's go and write that in. So plus negative x squared divided by 2 factorial n. Let's check out the third term. Minus, our next one's going to be minus 3 over 3 factorial n. 3 over 3 factorial n times x cubed. So it's going to be minus 3x cubed divided by 3 factorial n, because those n squareds are going to cancel with 2 of the n's on the bottom. So it's going to be minus 3x cubed divided by 3 factorial n. So minus 3x cubed divided by 3 factorial n. Minus, let's check the next one. Minus, it's going to be minus 6, and then these n cubes will cancel with 3 of the n's on the bottom. So it's going to be minus 6, and that says x to the 4, minus 6x to the power of 4 divided by 4 factorial n. So minus 6x to the 4 divided by 4 factorial n. And what's the next one going to be? Well, I'll tell you right now, the next one is going to be 10. So minus 10x to the 5. Oh, wonder if you can hear that plane or helicopter or whatever. Minus 10, definitely a helicopter. Minus 10x to the 5 divided by 5 factorial n minus, and I'm going to say dot 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 for now. How do I know that it was going to be a minus 10? Well, the reason why I know is because the next term on top, we're going to have n times n minus 1 times n minus 2 times n minus 3 times n minus 4. And that's all multiplied by x to the 5. So this is what our next term was going to be. And this was divided by 5 factorial times n to the power of 5. So how do I know it's going to be a 10? Well, basically, I'm going to be kind of adding on 4 to this one. And to get from here to here, I was going to be adding on 3 to this one. And to get from here to here, I was going to be adding on 2 to this one. And if you're not sure why that is, have a look at these numbers. Because remember, we're taking the number that's where n has been multiplied together 4 times. Has been multiplied together 4 times. So how many powers, how many different n to the power of 4s are we going to get when we expand this thing out? Well, have a look at these numbers. So the first one, there was only one of them. And then to get from here to here, there was another one of them. And then to get from here to here, there was another one of those terms. So we're minusing 3. And then for the next one, we're going to be minusing 4. So that's how we got to 10. So that's what's going on there. And then the next term is going to be minus 15x to the power of 6 divided by 6 factorial n. And the reason why I know that is because I'm going to be minusing a 5 off of that 10. So this formula can actually be written in another way. So this part down here, well, first thing first, I'm going to bring this negative 1 over n out because it's annoying me. I'm going to bring that negative 1 over n out. So this part underlined in red is actually equal to negative 1 over n times the sum, negative 1 over n times the sum, and we're going to start at 2. We're going to start at k equals 2. So times the sum from k equals 2, and we're going to go right up to n. We go right up to n. And then what do we got? Well, we've got x to the power of k x to the power of k, in this case k is 2, and well, our first one is going to be times by 1. Our second one is going to be times by 1 plus 2. Our third one, our x to the power of 4 is going to be times by 1 plus 2 plus 3, and so on. So maybe it was a bit confusing saying first one, second one, third one. So actually, our power of 2 is going to be times by 1. Our power of 3 is going to be times by 1 plus 2. Our power of 4 is going to be times by 1 plus 2 plus 3. And our power of 5 is going to be times by 1 plus 2 plus 3 plus 4. And so on. So actually our power of k is going to be multiplied by, and I'll do this in a different color, another sum. So it's going to be multiplied by another sum from, let's use a different letter, usually use j, from j equals 1, and it's going to be summed all the way up to k minus 1 of, well, just j. And this basically just says you sum together j's until you get up to k minus 1. So the first one, so if, so for example, say k equals 5, then we're summing from j equals 1 to 4 of j, and that's just going to be 1 plus 2 plus 3 plus 4. So that's what that means. And what are we dividing by? What actually goes on the bottom? Well, it's actually just k factorial, because we already brought out the ends. So that's all that's left of that part. We sum from k equals 2 to n of that thing. I know it looks absolutely hideous, but yeah, it's once you've seen it once and got familiar with it, you don't really need to think about it too much more. You certainly don't need to spend your life obsessing over it. So yeah, don't worry about how terrible it looks. It's not that bad. And we're not even going to need to worry about it in a little while. So this thing here can actually just be written as, well, I guess I'll write it as the sum from k equals 0 to n of x to the power of k divided by k factorial. So yeah, the first number 1, when k equals 0, you have x to the power of 0, which is 1, divided by 0 factorial, which is also 1. So that's fine. And then when k equals 1, you've got x to the power of 1 divided by 1 factorial, which is x. And so on. So actually, well, are we done? That's another question. Are we done? Because I actually might have forgotten something. Let's go back to our formula. Yeah, I forgot some stuff because there's actually other things going on. But to be honest, I'm not even going to worry about them. Why am I not going to worry about them? Because, well, for example, if I divide this in by this n cubed, I'm going to get n squared on the bottom. And that's a higher power of n. And remember, we're taking n as n gets very, very large. That's what we're going to be doing. So dividing by higher powers of n, they're going to disappear really quickly. Think about how big a million to the, think about how big a million cubed is. Think about how quickly that gets bigger compared to dividing by a million. So yeah, what I'm going to say for the rest of it, plus terms divided by higher powers of n. So we don't even really need to worry about that. So what have we got here? Well, we've got this thing. Let me use a new color just to highlight what we have got. We've got this thing here, which turns out to be just that formula there. And we got this thing here, which turns out to be this thing here. And we got terms divided by higher powers of n. So let's summarize that because it's a bit muddled at the moment. So what we have deduced so far is that 1 plus x divided by n to the power of n is actually equal to 1 plus, is equal to the sum from k equals 0 to n of x to the power of k divided by k factorial. So that was this first formula here. That's where that came from. Minus 1 over n times the sum from k equals 2 to n of x to the power of k times this other sum, times the sum from j equals 1 to k minus 1 of simply j. So we're timesing x to the power of k by that thing in the brackets, and of course that is divided by k factorial plus, and I'm going to say terms divided by higher powers of n, so n squared or higher. This one is only divided by 1 over n, so that's the one we should really watch out for, I guess, just in case that thing doesn't converge. Remember, what we're doing here is we're actually taking this thing and we're saying what happens as n gets bigger and bigger. What happens as n gets bigger and bigger? Well, let's check now. As n gets bigger and bigger, what happens? Well, as n gets bigger and bigger, these things here, these things are going to be controlled because they're divided by k factorial. Each of them are divided by k factorial. So these things are going to get really small as that k factorial gets bigger and bigger. So the part inside the brackets is controlled. It's not going to get too big as n gets bigger and bigger. So what happens when we divide it by larger and larger n is that it's actually going to get closer and closer to 0, just because the part inside the brackets is controlled. We're dividing by k factorial. As k gets bigger and bigger, those get huge. And so the part inside the brackets is controlled. It's not going to blow up or anything as n gets bigger and bigger. And therefore, since the part in the brackets, or now in the circle thing, is contained, when we divide it by n as n gets closer and closer to infinity, this whole thing is just going to get smaller and smaller. And so it's going to, we're going to say that it goes bye-bye. And same with terms divided by higher powers of n, when you're dividing by 1,000,000 squared or 1,000,000 cubed, it gets negligible. So these ones are going to disappear as well as n gets bigger and bigger. They're never going to entirely disappear, but since we're taking a limit here, the limit overall is going to get closer and closer to a number that doesn't really depend on these things. And so we're going to say that the limit, therefore, the limit as n tends to infinity of 1 plus x divided by n to the power of n, we're going to say that this is actually equal to the limit as n tends to infinity of this thing. And so it's going to be equal to what we're going to call the sum from k equals 0 to infinity of x to the power of k divided by k factorial. And again, this number is controlled, so that sum exists because we're dividing by factorials. We're adding something on each time, and whatever that something is it's getting really small really quickly because we're dividing by k factorial, and k factorial gets huge for big K. Think about 1,000,000 times 999,999 times 999,998 and so on. Yeah, so this thing is controlled, and that's what we're going to call e to the power of x. So our function e to the power of x is actually the limit as n tends to infinity of the sum from k equals 0 to n of x to the power of k divided by k factorial. So we just keep adding more and more of these guys on, and whatever they get closer and closer towards, that's what our e to the x function is. Let me just write that down one more time. So The definition we're going to use to differentiate e to the power of x is the following. E to the power of x, and this is the important thing that you really need to know, e to the power of x is equal to the sum from k equals 0 to infinity of x to the power of k divided by k factorial, and that's equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4 divided by 4 factorial plus ... It's equal to whatever this gets closer and closer towards, whatever number this gets closer and closer towards as we add more terms on. That's what e to the x is equal to. And I'll put that in a box because this is really what you need to take out of this lesson. Okay, thank you very much for watching. We're going to differentiate e to the power of x in the next video. Take care for now. Bye-bye.